You know that feeling, right? You're staring at a physics equation and suddenly there's this random letter that just pops up and throws you for a total loop. Or maybe you've tried to compare two things, say the speed of a bike versus a rocket, but their units are just from completely different worlds. Well, today we're going to pull back the curtain on all that. We're going to demystify the super powerful trick of unit conversion, and we'll uncover the really strange story behind a little constant in engineering called GC. Okay, so picture this. Your friend is just zipping along on their bike, right? And they're super proud they're hitting 60 kilometers per hour. Then they turn to you and ask, hey, how does that stack up against a rocket launching at 5 miles per second? And boom, instantly we have a problem. We're talking kilometers per hour versus miles per second. It's like comparing apples and, well, rocket fuel? They're not even in the same ballpark. All right, so here's our game plan for today. We're going to start with that bike versus rocket showdown. Then I'll show you a universal trick to solve it. And we'll even tackle those tricky units with powers. After that, we're diving deep into the mystery of that GC constant. So stick with me, because by the end, you're going to see why this is so much more than just numbers. It's about learning to think like an engineer. So first things first, how on earth do we actually compare these two? Well, it turns out there's this one incredibly powerful trick, and it works for any unit conversion you will ever have to do. And I mean it, any of them. Let's break it down. Okay, it's a method called unit cancellation. And honestly, it's a beautifully simple four-step process. First, you just start with what you have. Then, and this is the cool part, you multiply it by a clever little fraction, which we call a conversion factor. The whole trick is just arranging that fraction so the units you don't want literally cancel each other out, leaving you with only the units you do want. After that, you just do the math. It's really elegant. So let's put this into practice with our bike. We start with 60 kilometers per hour. Now we want to get rid of kilometers, right? So we multiply by a fraction that has kilometers on the bottom. In this case, 1 mile over 1.61 kilometers. And just like that, boom, the kilometers cancel out. We do the exact same thing for hours. We put 1 hour on the top to cancel the hours on the bottom and 3,600 seconds on the bottom. The hours just vanish. And look what we're left with. Exactly what we wanted, miles per second. Okay, so we crunch the numbers, that's 16 divided by 1.61, and then divided again by 3,600, and voila, we have our answer. The bike is moving at a blistering 0.01 miles per second. And this is where it all just clicks. I mean, look at this chart. You see that tiny little sliver over there on the left? Yeah, that's our bike at 0.01 miles per second. And that towering bar on the right, that's the rocket at a full 5 miles per second. Now that they're finally in the same units, the comparison is it's staggering. The rocket isn't just a little bit faster, it is on a completely different planet of speed. Okay, that was straightforward enough, right? But what happens when our units get a little more complex? I'm talking about units that have powers, like area in square meters or volume in cubic feet. This is where things can get a little tricky if you're not careful. All right, new challenge for you. Let's say we have an area of 45 square meters, and we need to figure out what that is in square centimeters. Now, it seems simple enough, doesn't it? But trust me on this, you gotta be careful. There is a super common trap here that catches a lot of people. Okay, so here is the absolute key, the one thing you have to remember. You can't just convert meters to centimeters. Why? Because our unit is squared. That means we have to square the entire conversion factor. Think about it for a sec. A square meter is just a meter times another meter. So when we convert, we have to convert both of those meters. So we take our little fraction, 100 centimeters over 1 meter, and we square the whole thing. That means the 100 gets squared to become 10,000, and the units get squared too. And that is the correct conversion factor we need to use. All right, so I think it's safe to say we've mastered the art of conversion. So now, let's venture into some truly weird territory. We're going to tackle something that has legitimately confused engineering and physics students for generations. I'm talking about a mysterious constant called GC that sometimes just appears in our equations. So, you probably spent years learning Newton's second law as F equals ma. Simple, right? Elegant. Then, one day, you crack open a textbook and you see this. Force equals mass times gravity, all times divided by GC. Wait, what? It's like you're playing a game you've known your whole life, and suddenly someone just throws in a new rule completely out of nowhere. I mean, this just begs the question, right? What is this GC thing? Is it some fundamental constant of the universe that we just never learned about? And maybe even weirder, why does it only show up some of the time? Well, the answer, as it turns out, has very little to do with deep, complicated physics. It's actually a story about history. And it all comes down to a simple, but pretty profound, mix-up that happened a long, long time ago. Okay, and this is where the mystery really deepens. In the metric system, the SI units that most of the world uses, GC is just 1. It's basically a placeholder. It does absolutely nothing. But in the old foot-pound second system, the FPS system, it has this bizarrely specific value, 32.174. That is not a random number. So what is going on here? So to unravel this whole thing, we've got to understand two key terms from that old FPS system. First up, we have the pound mass, or LBM. Now, this is a true unit of mass. It's a measure of how much stuff an object is made of. Your mass is the same whether you're standing on Earth or you're jumping around on the moon. And then we have the pound force, or LBF. And this is critical. This is not mass. This is a unit of force. To be specific, it's the force of gravity pulling on an object, what you and I would just call its weight. And of course, your weight changes depending on where you are. Mass and force are two fundamentally different things. And right here, this is it. This is the source of all the confusion. The engineers who first developed the FPS system were, well, let's just say they were a little careless with their definitions. They used the exact same word, pound, for both mass and for force, completely blurring the line between two very, very different things. And when you do that, well, you create a huge mathematical mess in your equations. So here's the big reveal. GC isn't some deep, universal constant of nature. It's a patch. It's a Band-Aid. It's a man-made correction factor that was invented simply to make the math work in a system that had a fundamental flaw baked right into it. That number, 32.174, it's not magic. It's precisely the number you need to correctly convert units of pound mass into units of pound force. It's a brilliant, but let's be honest, ultimately clunky fudge factor designed to fix a historical mistake. So, after all that, you might be wondering, why does any of this matter? I mean, we've gone all the way from bikes and rockets to weird historical mix-ups. Well, it matters because understanding the why behind the tools and equations we use, that's the difference between just blindly plugging in numbers and truly deeply mastering your craft. So let's lock in the main takeaways from all this. First, unit cancellation is your universal go-to tool. It works for everything. Second, whenever you see units with powers, remember to apply that power to the entire conversion factor, the numbers and the units. Third, GC is not some law of physics. It's a man-made fix for the FPS system's old confusion between mass and force. And finally, and this is probably the most important one, knowing the story behind an equation helps you avoid making those critical, real-world errors that can have really serious consequences. And all of this leaves us with one final, kind of fascinating question to think about. GC was a patch, right? A clever fix for a flawed system, hiding in plain sight inside our equations. And it really makes you wonder, what other historical quirks or compromises or little fixes might be embedded in the science that we take for granted every single day? Something to think about. Thanks so much for joining me for this explainer.